All right. It looks like the numbers in the waiting room are slowly decreasing. So I take this as a sign that we can get started with our workshop today. As soon as I find the right screen to share, which should be that one. Hopefully an LCE screen.
Yes, we
Yes.
can see it.
Perfect. Okay, so welcome to our workshop today, Unlocking the Potential of Data, Fair Data Principles in NFDI, brought to you by Physical Science in NFDI, a workshop series where we want to showcase and highlight use cases for tools, for solutions, for research data management coming from the 7 consortia that are involved in physical science in NFDI. My name is Michael Liebau from Universität Leipzig and NFDI FACAT. And before we get started in the use cases themselves, allow me to start with a short introduction to the topic with the classic question, why doesn't the screen move? Yeah, the classic questions, why do we need fair data? And fair data, of course, referring to the FAIR principles, meaning that data should be findable, accessible, interoperable, and reusable. And especially in the natural science, but also in engineering, that often we have to differentiate between fair data and open data because there can be restrictions, there can be industry corporations, for example, coming up, or patents or other points of intellectual property. So fair data is not necessarily open, but as open as possible, but as close as necessary. And the FAIR principles are about retaining the full value of the data sets over time, so independent from the individual researchers that created the data sets in the first place. And of course, there are many advantages to fair data for the researchers themselves. Fair data management means they have a means also to structure their research workflows. It saves time in the long run, not having to repeat experiments, being able to build up upon existing projects, existing research already. And apart from the reusability, also the publication of this data is usually possible with much lower effort if it's already provided in a fair format. For institutions, there are advantages. It's a matter of quality assurance and also about effective use of resources in the end if experiments do not have to repeat it all the time, if previous projects can be used. It's often demanded by policies, and of course, it's an important criteria for funding also. And last but not least, from the scientific community as a whole, it's about transparency, about making science itself transparent and being able to reproduce results easily. So I would say in the last couple of years, the question actually shifted in the communities from why do we need fair data to, well, how can we get this fair data in the end? Because right now, in catalysis, but also other communities, we still have a situation where most of the data that is being created, and it's getting more and more every day, is actually not used anymore. Some is published in journals, some is made available as fair data, but a large amount of it, my own PhD thesis a couple of years back included about 60% of this data was never used again. Um, yeah, and of course, that's a situation that we need to change, but there are reasons for that. There can be a limited willingness to actually share the data, but there are also technical reasons like infrastructure that is just emerging now to effectively share this data. Often the data is present in unstructured formats or proprietary formats, especially in our community in catalysis. We often have measurement setups that are tied to specific renders with very specific data formats that can be a hindrance in sharing the data. And the documentation of the data is often done in a local way, in a non-standardized way. And even if data is shared, we often find still something like this, just a picture. In this case, it would be the conversion of some catalysts over temperature, and why it would be possible for a human to take out a ruler from a cabinet and somehow estimates individual data points. Well, for machines, that's a completely different topic. So this data cannot easily be analyzed or integrated with new research data. And the machine readability itself is heavily hindered, at least for the technology as of yet. So we have to move away from this perspective, from this unused data to a future, to a situation where most of the data is actually made available as fair data, is available for reuse and for further scientific purposes through common standards, through structured data to quality assurance of the data sets, an established infrastructure and persistent identifiers that makes this data findable. So this data can be used. Of course, there might be still restrictions. There might be possibilities that the data will be only shared after a couple of years, but at least the value and the understanding of the data set is still present. However, there are still challenges in this regard. And one of the challenges is in the FAIR principles itself. And FAIR principles, by their core definition, are actually rather technical. It's about finding the data sets, being able to use the data sets with existing technology and having access protocols that work, but it's not so much in their core about the quality of the data, the real scientific reusability in the end. And that's, of course, a mission of the NFDI, one of the core missions, to transfer those FAIR principles into the disciplines and address these aspects of the data quality, to bring it in a perspective of the respective disciplines of science. Through metadata is important here, of course. What metadata exactly is needed for data sets for further understanding how this documentation with the metadata can be done in an efficient way. Of course, we all want ideally all information available to be present with the data set, but we also know in practice that rarely works because it's just too much effort for individual researchers to provide all the extra information that might be necessary. So it needs to be also automated. It needs to be integrated in a machine actionable way, ideally in existing workflows with low effort, or creating new workflows that do not change too much the way that we do science right now, because also scientists are creatures of habit. And in the end, the FAIR principles, of course, fairness itself should not be a purpose by itself. It's not a matter of just checking somewhere on a DFG checklist that we have fair data. And while reproducibility of experiments is already a nice start, not having to do everything again and again, there are many more benefits that can be highlighted and that can be created from fair data sets, prediction of new materials, for example, AI-based approaches. Okay, but I actually promised you that we would get a bit more in practice in use cases. So we don't want to talk about the FAIR principles in general. Want to see them in action. And for that, I would like to give the screen directly to Lukas Pielsticker from Fermat, who can maybe show us how this FAIR data can be created and integrated in NeXus. Please, the screen is yours.
All right, I hope you can see this properly. Then we can start.
Yes.
Right, yeah, thanks for the nice introduction. This actually takes away a bit of what I was going to talk about, and this then helps me getting into the topic much more easily. So what I will be talking about today is our efforts in standardizing experimental data in solid-state physics and material science using the existing NeXus standard from the community. And what I want to highlight here is that it's not just an effort made by myself, but I put intentionally here the Fermat team, because this has been a long-going effort for a number of years now within the Fermat team, and it has really been a team effort. So, yeah, just as a reminder, what is Fermat and what are we doing? So we are the consortium tasked with building a federated data infrastructure for solid-state physics and material science. Fermat organizes itself into various task areas. Some of these are on scientific topics like data infrastructures for synthesis and computation. And one of these scientific data infrastructures data areas is focused on experiment, and this is the one that I have been working in. So this is really about characterization data in material science and solid state physics. So if we look at material science and specifically on characterization techniques in the field, we see that we have a very broad and interdisciplinary domain. So this really goes from ad hoc experiments done in the lab using, for example, just materials that you have in the lab and then assembling them ad hoc. And then you go towards more automated systems like you would have in the lab, which is a very complicated system producing higher amounts of data. And then even towards large facilities like synchrotron and neutron sources. And what really this means is that we have different data practices across the community, and we have diverse experimental techniques and workflows. And what this also directly leads to is that we have very heterogeneous data and metadata requirements in the community, and even across data recording, but also about data scale and so on. And if we just think about data formats that we have in the community, so what we see here is I just pulled some of the data sets that we acquired or that users gave us over the years, and we see that there's a large amount of very different and diverse file formats. There's a variety of open and closed formats, and there's a lot of instrument-specific data structures and metadata. And really, a lot of the data formats are not well reported at all, so it's very hard to understand what is in them. Sometimes they're even proprietary, and this often leads to vendor login for the different working groups. And then additionally, we often have very inconsistent reporting practices. Some facilities and instruments produce a lot of metadata. Others produce much less metadata, and it's often very hard to understand what the actual data means that you have in your files. And one of the reasons why this is the case is because there's basically in most of these fields, there's basically no metadata standards or no way of standardized reporting that you should do for your data. And what this basically means is that a lot of the file formats that we see in the community are essentially black boxes. So this really means that we have very limited interoperability across domains and even inside domains for different vendors, for example. And this produces a lot of reproducibility challenges when you try to remeasure, for example, on a given sample. And what this really means is that in the solid states community, there's a need for open formats which have a standardized metadata structure. So this is what we set out to do in Fermat from the beginning of Fermat 1, is essentially producing standardized metadata schemas that can be used across different instruments, facilities, and across different domains. Of course, I think many of you will be familiar with this sketch from KCD, which is that if you try to produce a standard, it can be very easy to run into the problem that you just produce another standard and then you have one more standard in the field, but you actually didn't improve the situation for the users. So what we in Fermat did is that we didn't start on producing something really from scratch, but we searched in the community what was already there and then tried to build on top of this. And this led us to use the NeXus community format. So NeXus is a common data format that has been around for over 30 years, and it originated at large scale facilities, so neutron, X-rays, and muons, and so on. So really much closer to what, for example, Daphne for NFDI is doing. But what we have done is extended this to a much broader coverage of material science. And by we, I don't just mean Fermat, but also other people from the wider scientific community. And what NeXus provides is a community-driven open standard for reporting data and metadata in these fields. And the advantage of using NeXus is not just that you provide some sort of data format, but this is really maintained by an international community. And there's even an advisory committee that maintains the standard going forward. So what does NeXus actually define? So NeXus defines a hierarchical structure for your data and metadata using group fields and attributes. I will explain this in a minute more. And then there's basically two things that NeXus defines. These are the so-called base classes, which are glossaries of terms for instrument components like detectors, sources, beams, and so on. And then in addition, it defines application definitions, which are essentially metadata schemas for a specific experiment type that people can then use for their own data. And really what this is all about is giving conventions for how to name things, how metadata should be structured, how which units should be used, and how data should be linked internally. So here's an example that I basically wrote myself. It's not an official NeXus definition, but it's just to give you a bit of information. So this is about a double slit experiment or a hypothetical double slit experiment. And what you see is that NeXus essentially creates a hierarchical structure using grouping, which essentially represent the experiment structure. So we see here then you would have an instrument in there, which contains a source, the double slit that you would have in your double slit experiments, the detector that actually measures the electrons that you would be interested in, and then also the actual data that you would get. And then in there you would have so-called fields for numerical data and metadata, which is essentially defining what a wavelength is for this particular experiment with units and the physical meaning attached. And then finally, there's also attributes for describing the context, for example, units, the signal that you measure, which axis your measurement has, and so on. And then really this is just a metadata standard. So this could be serialized in any format essentially. But often what ends up happening is that the serialization of NeXus data is then done in HDF5. And I will show some example later how this actually looks like in HDF5. And as I've said, so NeXus really gives you two kinds of definitions. So one is what we call the base classes. So base classes are really describing one instrument component or one idea also essentially that is part of your measurement. And then inside the NeXus base classes, this is actually a collection of terms, so a glossary on how things in for example, here in an example, so in a sample system, should be named. So we have things like name, sample ID, the chemical formula, but then also things about the environment of your sample, how the sample is composed of different other components, and so on. So there's a number of NeXus base classes that really are used across the whole NeXus system, and this makes it interoperable also across domains. And then, of course, there's a lot of description of components like detectors, manipulators, mirrors, and so on. But also you can describe with NeXus things like fitting, calibration, the coordinate system that you're working in, affine transformations between different components of your system, and so on. And then once you have defined these base classes, what NeXus additionally provides is so-called application definitions. These make use and also specialize these base classes. And what they really do is that they collect the required, recommended, and optional metadata needed to understand a given experiment. And that basically means that once you have an application definition, this can be the community standard for a given experimental technique. That means that once you are using such an application definition for your own data, others can understand the data well, because this is given, or basically because you have to supply the required metadata, and then this is easy to understand what the experiment actually means. And then these application definitions really act as a contract between the data providers and the consumers. So both the data providers and the consumers can be sure that if they use the next application definition, that they understand each other even after the experiment has been done and even after the data has been transferred somewhere else. So I was talking a bit about how NeXus is actually a standard, and I think it's very important to understand how NeXus actually becomes a standard. So it's not just that you provide some metadata formats and agree basically with your coworker, but it's also about agreeing with the whole community on what experimental metadata you must provide to be part of this standard. So how does this actually work? So the first thing is often that somebody in the community, like we did also in Fermat, proposes a new base class or application definition to be added to NeXus. And then there's a lot of open discussion and peer review going on in NeXus meetings. They also have teleconferences about once a month. And most of the discussion actually happens in the open on GitHub. And then based on the feedback that you get there, you have an iterative refinement. So at the first, for the first year or so, that you typically have a contribution phase where you have these, your community proposal contributed, but then people can refine it and give iterative feedback and so on. And then once people are happy with it, you can present this to the NeXus International Advisory Committee, the so-called NIAC. And the NIAC is made of various members from large-scale facilities, but also smaller facilities across the globe. So that really represents this, a subset of or a representative subset of the global community in this field. And then the NIAC will, of course, technically review your proposal for consistency with the NeXus standard. But then what they will also do, and I think this is the most important part of this standardization, is that there will be a formal vote by the NIAC, which essentially represents facilities across the world, so that you can be somewhat sure that this is also accepted by a large part of the community across the globe. And then once this formal vote has happened and there has been acceptance, then this gets then your application definition or base class gets included in an official NeXus release, and then this can be used by everybody else across the community. So what Fermat set out to do already at the beginning of when it started is that we decided to build standardized metadata schemas in NeXus for subsets of methods in material science. So this includes photoemission, electron microscopy, atom probe tomography, optical spectroscopy, but also scanning probe microscopy, for example. And then what we did is that we built base classes and application definitions in NeXus to be able to represent data from very different data sources. So really, we looked at the data that was existing in the community, looked at the metadata that was reported there typically, and then we tried to build a format that encapsulates a lot of the existing vendor formats, even existing standards that are out there for some of these fields, synchrotron data, but also what data analysis software would produce. And then we try to build encapsulating metadata schemas that would be applicable for all of these. And Fermat contributed over the time a lot to the NeXus standard itself. So it really, because of Fermat, the NeXus standard has grown quite a bit. So we contributed 20% of all accepted application definition, about 60% of all accepted base classes. And then there we also have a lot of more contributions still in this contribution phase that I described earlier. So really, Fermat extended the NeXus format from this community based on X-rays and neutrons towards a broader fields of material science. And of course, we didn't just come up with these standards alone. So really what we did is we tried to engage the community. So we ran a series of what we call technology partner workshops at Fermat headquarters in Berlin, where we try to invite as many instrument and data providers and also scientists from the community to discuss these metadata formats and the standards that we want to propose. So here you see just a subset of the companies and facilities that we engaged. And then really we collected and integrated a lot of the feedback that they gave us. And we also tried to open direct communication channels to the technology partners so they could give us feedback directly. And the idea is really that eventually they may be able to adapt these standards themselves and report their data directly so that people can work with the NeXus data directly. What we also did is we didn't just talk to them, but we also developed data converters and examples for the existing formats for a lot of these data providers, a lot of the data formats coming from instrument vendors and so on. And I will talk in a bit in how broad this coverage is actually in the data conversion space. So here's just a number of examples of the metadata schemas and the actual data that we provided. So here's this for photo emission, where we really try to build one NeXus schema for all data in photo emission spectroscopy. So this is able to encapsulate multidimensional data, but then also it can represent data analysis done by software, and we can even pass this data analysis here, for example, peak fitting in X-ray photoelectron spectroscopy. And then since we have this unified metadata standard, we can even build like search applications on top of it. And I will show a bit later on how we do this. And what we also try to do in photo emission is that we provided parsers for most instrument used in the community. And this is even applied in multiple labs across Germany and tested in the companies that we engaged earlier. Another example is electron microscopy. Here we also did a lot of work to try to build one NeXus standard that can really showcase all the data acquired with electron microscopies across the globe. So really this one standard can contain data from electron microscopy imaging, yield spectroscopy, so spectroscopy that you do in your microscope, and even diffraction data. And also here we have a lot of parsers for instrument formats across the community. So maybe just a bit of what we learned in standardization. I think this is very important for other people who want to do similar or want to go a similar route. So really what I can only advise people to do, if you want to do some sort of standardization, you should start as early as possible and try to engage as many partners as possible to build something that is then actually reusable for other people. And then also, if there is a standard committee, for example, like we have in NeXus, then it's very important to participate in the meetings, in the workshop and teleconferences, so on, both to get feedback, but also to gain trust from the actual community that what you're building is actually useful for them. Another thing is that you should, or that it's very helpful to provide use cases that showcase that your particular standard is actually useful for the data that other people would have. And this is maybe a bit particular to NeXus, but I think it applies to a lot of standards. It's often very much easier to add to a given standard than to change how it fundamentally works. Often it is very important to respect existing standard and not to roll over what other people have done in the community and just say we want to do our own standard, because then eventually you end up in the situation that you build something yourself that nobody else will use, and then we just have another standard to the existing 15 standard that already exists. And often it is possible to even do like changes to the core of standardization frameworks, but this really requires a lot of convincing and discussing, and even just it's a time matter that it takes a lot of time to convince people that a given change is important. For example, in NeXus, it was for a very long time hard to convince people that it's important to also allow inheritance between base classes and so on. But over time, since we did a lot of the convincing, this then became possible, and we use this now quite frequently across our standards. So as I said earlier, it's important to not just build metadata standards, but also to build tools that can actually make use of these. So here I'm just showing one of the tools that we are building, which is called PyNX tools, so Python NeXus tools, which is our all-in-one NeXus tool for working, a FEMA tool for working with NeXus data. So this is about data conversion, data validation against the NeXus standard, inspection of NeXus files, and this also acts as a plugin to the Nomad platform, as I will show in a minute. So really, you can install this as a Python package, and then you convert existing data from a given community format to the NeXus format. And how this works is that here I'm just showing a bit of how the workflow is. So we produce a lot of raw data as shown in the lower left. Then you have a lot of automated metadata from this instrument and a bunch of manual metadata from electronic log notebooks. And then you use a reader or a parser to pass this information into the NeXus format. And then you have a validator that makes sure that it's actually compatible with the given NeXus standard. And this then allows you to build containerized tools around these, because once you have the standard, it doesn't actually change anymore. So any file that is in the standard can be used in a standardized manner as well. And around this PyNex tool system, we also built a plugin ecosystem, which uses the Python plugin system essentially. And this allows you to build individual converter tools for files from different domains. So here I'm just showing a bunch of the domains that we have been working in to build parsers to support a large subset of existing format, at least for some of the techniques that we are in. And this is really meant to be adaptable and scalable. So we provide templates and documentation so other people can use this as well. Okay, so the other thing that we are of course, doing in Fermat, and I think this is mostly what Fermat is working in, is that we built the Nomad platform. So I think a lot of you will heard about this. So this is a web-based software for fair research data management and material science, which provides a lot of tools for data sharing, publishing, and making their data fair. So what we also did with the NeXus format is that we fully integrated this into the NeXus, into the Nomad platform as a so-called Nomad plugin. So Nomad has its own plugin system, and the PyNex tool software is just another plugin to the Nomad software, essentially. So what we provide is the NeXus schema in Nomad, a parser for NeXus files. We have the data converter there running directly, and then we can also do visualization, search, and exploration in Nomad. So in Nomad, what we actually have is our own metadata schema, which is called the Nomad meta info, which is combines a domain-independent superstructure with detailed method-specific data description. So what we can do is extend the Nomad meta info with the NeXus schemas, and then we can work with NeXus data directly in Nomad. So here is what we did. We basically mapped the schema from NeXus, which we show on the left, which is shown in, which is usually done in XML files, to the Nomad meta info shown on the right. And then this allows us to actually get all the schemas that we built in NeXus into the Nomad platform. So here we see all the terms that are defined in NeXus passed into the Nomad meta info platform. And then you see here, for example, the description of fit. And then this has subsections, for example, for peaks and so on. And then once we have this schema available in Nomad, this also allows us to automatically pass NeXus files, but also data from the community using the data converters that I showed earlier. So here I just dropped a NeXus file into Nomad, and then then Nomad automatically understands the content of the NeXus file and passes this into the Nomad's meta info schema. So here we see we can have a look at the NeXus data as it was uploaded in HDF5 files, but also we pass this into a structured schema, which can be then later used for visualization, for search, and for exploration. So this is an example of an XPS measurement, but this can be done for all kinds of measurements that are described by NeXus. And then since we have this metadata structure shared across experimental techniques, this allows us to build search applications where we can search through all the NeXus metadata metadata in Nomad, and we can even filter by instrument and samples, or we could also filter by the elements that were present in a given sample that was measured. And then this filters the whole NeXus data that we have in Nomad, and then you see here again all the data that was uploaded, and you can explore individual entries as well. And then finally, in Nomad, since we have standardized metadata, we can also run standardized tools. So in Nomad, we have something called the Remote Tools Hub, where we can run remote tools as containerized Deborah applications. And since we have this standardized metadata, for example, we can here run a specific Igor script that really takes care of, that really uses the NeXus schema, and then can pass any data that we upload to Nomad in the NeXus format. And then finally, how do we bring this to the community? So I said earlier we had this technology partner workshop for building the standard, but now we also want to bring this to the community. So we do a lot of workshops at large facilities, but also at individual user groups. We do hands-on sessions. We collaborate with instrument scientists and facility staff across the Fermat community. And then we also do a lot of user support and onboarding, really to connect us to both the wider NeXus community, but also the material science community in general. And then maybe as a bit of an outlook, what will we do in the Fermat second phase, which will start in October? We will build on the lessons that we learned earlier to broaden the scope to more experimental methods, and then also provide high-quality data sets that other people can use in the future, and then also for AI-based reuse of this data. So with this, I'm done, and I would like to thank you for the attention and all the Fermat co-workers for building this.
Yeah, a lot of digital applause coming up. Thank you very much for this very interesting presentation. I think we have time for a couple of questions. Before we get into this, I should also mention, since this session is recorded, A, I should mention that the session is recorded, and B, if you do not want to show up, if you do not mind showing up in the recording, please feel free to just raise your hand and ask your question as usual. Otherwise, you can use the chat. If you still want to talk with our presenters and do not want to be recorded, also in the end of the session, we will have some time for discussion where we can turn off the recording. All right. And I see already two questions in the chat. One is, can you comment on how much vendors are willing to actually participate in the development and using the NeXus standards, including natively exporting the format and so on?
Yeah, so I have to say it's very much a mixed bag. It really depends on the company itself, how oriented they are towards industry, or for example, more towards research. So the more research oriented they are, the more willing they are able to, or they participate in the development of this standard and also using them. I have to say, a lot of the times, what they were looking for is actually to do this standardized format so that they can produce an exporter, for example, once, and then they are done with it because the format would not change anymore. But it's also often these companies work on different timeframes than what we can do. So we are still, for most of these companies, in the convincing phase than to say exactly that they can export this natively. Some of them are building things like this, and some of them can already do this, but it really depends on the company.
All right. We also have a second question. How do you limit access to data in terms of IP? I assume that's referring to the Nomad part that you showed.
So there's basically two kinds of Nomad out there. So there's the central platform where you upload data, and there you have this is really about publishing data for the wider community. So, for example, if you write a paper, then you publish your data with it. And then we have this second layer, let's say, of Nomad, which is called Nomad Oasis, which runs the same software but on your premises, and then you can really control what you do with your data, who gets access, and so on. So this is really about local lab management, and then this is also you are protected from, or your IP is protected from being leaked to the outside. So on the central Nomad, I would say this is really for data that can be published without any IP concern, but Nomad Oasis can be used also if you have IP sensitive data.
All right, thank you. I don't see any other immediate question. If something comes up, you will also have the time in the end to continue this discussion. But for the schedule, I would say we'll come to the next use case now, which is coming from Punch for NFDI now with Hubert Simma about fair data for lattice gauge theory and beyond. Please, Hubert, the screen is now yours.
Okay, I hope you can see the screen and
Yes.
hear me. So thank you for this opportunity to report a little bit on how in how theoretical physicists in Lattice QCD started to do fair data management for their data. And of course, this is I'm reporting this also on behalf of the International Lattice Data Grid, of the working groups there, and on the other part on the various contributions which came up in the Punch for NFDI consortium. So I would first like to briefly give a short idea of Lattice QCD in a nutshell, and then explain the background of this our initiative to sharing lattice data, the International Lattice Data Grid, and then get to more technical aspects of the new features and possible extensions of this setup. And because I have to say, my talk is much more on the technical side than on the metadata side, and I hope it will also be clear why this is the case in a moment. So why do we need QCD, or where do we need lattice QCD? Typically in high energy physics experiments, like at CERN, or in other cases also nuclear physics experiments partially. In order to interpret or analyze these experiments, one needs to know some quantities which are purely determined by the strong interaction, by the strong force, which is called quantum chromodynamics, QCD. Quantities as simple as maybe hadron masses, but also more complicated quantities like decay constants or form factors, etc. And these quantities are formally in QCD defined by a path integral. This is an integration in an continuous infinite dimensional space. So even mathematically, this is not really tractable and well defined. So one considers space-time as discretized on a finite lattice, and then this integration becomes finite dimensional, as many dimensions as you have lattice points. So suppose you have 100 points in every direction. That means that you have at least 10 to the 8 dimensions for your integration, for this integration. And the only way to do such integration or integrals is a Monte Carlo method. So you represent your quantity, which is this integral. You approximate this integral by simply an average over a suitable sample of sample points. These sample points, these CIs, these are what we call field configuration. They correspond to the field values of the gluon or of the quark fields or of other particles on every lattice side, and these are essentially vectors of length 10 to the 8, 10 to the at least 10 to the 8, or as scaling with the volume of your lattice. And then you have two terms. You have an exponential factor, which looks a little bit like a Boltzmann factor, which basically contains the whole definition of the theory. And then you have another factor which depends on the quantity which you want to measure, whether it's a mass or decay constant. And then, of course, you have to take the limit of a large sample size of your Monte Carlo estimator. You have to make the lattice spacing to 0, the physical volume to infinite, and masses and any parameters to the physical parameters. So there are a lot of limits which you have to take. So you have to repeat this kind of computations several times. And each time this computation consists of two steps, basically. First, and that's why the name simulation comes from, you perform or you simulate a Markov chain in order to generate these configurations, these vectors, according to this strongly peaked exponential distribution. And this is a relatively sophisticated algorithms which you need for this Markov chain. But this is essential because otherwise, without important sampling, this Monte Carlo estimator would not converge in a reasonable way. And since it's a Markov chain, it means that each configuration or each step depends on the previous one. So you have a long dependencies, and you have to generate these configurations one after the other. And then in the second step, you carry out the measurement of these quantities of interest on these individual configurations. So how this looks in practice, and in order to give also order of magnitudes of this process, so this throwing the dice, generating this Markov chain produces this primary data, and this is in terms of an experiment, it would have a very low event rate. Something typically you would get one configuration every 50,000 core hours. You don't want to wait for that a long time, so therefore this kind of computation is done on leadership supercomputers like the Lumi or the machines in Jülich or in Munich. And then in order to generate a typical ensemble, then therefore also the cost either in euro or in kilotons of CO2 gets sizable. And the data volumes, because you want Monte Carlo samples of at least 1,000 to 10,000 per parameter set, individual configurations are between 1 and let's say 100 gigabytes, then you easily end up with data volumes of petabytes. And of course, this intermediate data or this primary data is then highly reusable for different measurements by different projects, by different collaborations all over the world, sometimes even a decade after being produced. And then, of course, these measurements can be done typically on local PC clusters, because you can also then measure, basically, if you have enough machines, completely in parallel on each of these configurations. So before going to the setup, how the Lattice community decided that this precious data should be shared, what are the requirements for this sharing? Of course, the sharing should make this data fair or compliant to the FAIR principles. I don't have to remind you also, FAIR principles are very concise guiding principles. They don't tell you about the implementation, how you achieve it, but it's probably useful every month to go. This is 15 points formulated by Wilkinson in 2016. A key point is the globally unique and persistent identifiers, rich metadata, and then the fact that the data and the metadata is registered and can be searched in some registry or in some device, in some catalog. And also the fact that it should be accessible even when the large data is happens to be not available anymore. And this, in our case, brings additional requirements. So the fact that we have large data object means that the metadata should be stored, at least in addition to the combined with the data, should also be stored separately in a catalog. It can be included in the data objects in HDF5 files or whatever format you use for packing. It could be included in the data for convenience, but it also has to be stored separately in order to make it searchable. And since the Lattice community is a small community, probably compared to what we heard before, but still it's a worldwide distributed community with worldwide distributed infrastructure. And therefore, we have to deal with multiple service provider, multiple institutions and communities, which gives an additional challenge for implementing such a system. And then, of course, physicists not always want their data immediately publicly available. There could be embargo restrictions, and certainly write operations should be carefully controlled. So one needs also on such a global system some fine-grained access control. So compared to a local implementation of a FAIR data management, which you could have on your laptop or in your email box, that's basically a FAIR fair data management system. You have an IDs, you have metadata and data. You can have them in any way, any form of a database, formally or logically, with three fields: IDs, ID, metadata, and data. For larger data objects, you have to split this into a metadata catalog and data storage system. And if you also want to have replicas or storage locations which might vary in time, then you also need a file catalog which provides the mapping between these persistent IDs and the current, possibly multiple storage URLs of your data. And as we said, we need to have a rigorous access control, at least for accessing, for writing the metadata, for changing the file catalog, and for changing or creating or deleting the actual data. And this is roughly the setup or the idea where the International Lattice Data Grid started more than 20 years ago. And following the advice which we heard in the previous talk to start early, the first big and major achievement of ILDG was definition of a community-wide, rather rich metadata schema in 2004, and then also setting up a kind of an infrastructure and services a few years later, which completely degraded over the years and have been strongly and thoroughly modernized in the last few years, thanks to also the activities in Punch for NFDI, and which I explain in a moment. But before that, maybe a little bit on the idea, on the organization of the ILDG. It's actually, we call it a federation of autonomous regional grids. There are the different communities in the US, UK, continental Europe, Japan, Australia, and they form a single virtual organization, but actually have a large degree of autonomy in implementing services and implementing the infrastructure. And ILDG itself only defines or handles the user management and the definition of the standardized metadata schema, the file formats, and the APIs of the individual catalog services and storage services, for instance. And this is done in two working groups: the metadata working group for the definition of formats and metadata, and the middleware working group for, let's say, for defining the APIs and the possible implementations of the infrastructure, and of course a board. And then the regional grids actually provide the catalog services and the storage with their specific policies, technologies of choice, and also resources, of course, from national funding, for instance. And in the European regional grid of ILDG, we made also very much use of technologies and services of the WLCG, of the worldwide LHC compute grid, which from the high energy physics community, of course, is the closest community. I don't want to go deeply into the metadata schema. We actually have two metadata schemas, one for the individual data objects and one for collections or for data sets, which in our case means data objects or configurations which are produced in a single Markov chain simulation, because they share the same simulation parameters and a lot of common information about physics, about the algorithm which was used, the provenance of machine codes, etc., which were used, and the actual data management. And I would say it is a relatively rich and deeply hierarchical metadata schema. This on the right-hand side is just an illustration of the part which describes the physics of the quarks. And it defines of the order three to four times more elements than, for instance, the celebrated DataCite metadata schema. And what we had recently was an update and an extension of this metadata schema in order to make it fully FAIR compliant and in order to incorporate a number of user requests, because in the last 20 years also the physics and the algorithms to be used have been changed. And I mean, this is the advantage of the design of this metadata schema to be intrinsically extensible in a way that also metadata produced 20 years ago still validates, but can extend the metadata schema to take into account new developments from the physics or on the algorithms. And the point which was missing to make it FAIR compliant is that we didn't have a mandatory license statement. But apart from this, I think this ILDG setup was almost FAIR compliant even more than a decade before the term FAIR was defined. So this is it's quite nice to see how consistent this was already 20 years ago. And in ILDG, we still stick to XML as the preferred format for our metadata for various reasons, because it's a W3 standard. It allows a rigorous definition, it has a rigorous definition of the grammar of the metadata. And it also has allows for powerful and complex search through XPath, through XQuery, and there are many tools and libraries existing for building clients, etc. What was a key development within Punch, and that's why this is earmarked here with two logos. The critical contribution possible through Punch was the complete refactoring and setup of new catalogs, the metadata catalog, the file catalog, and also an auxiliary access control service. And in particular, this metadata is now completely can support multiple collections of metadata, and each collection of metadata is completely free configurable with its own metadata schema. Metadata is always strictly validated before it is inserted in the catalog, and it supports this relatively complex queries through XPath, but also through other search mechanisms. And this is now in a relatively convenient containerized implementation. And in fact, this allows that the different regional grids basically are all in Japan, in UK, for instance, now simply have deployed or redeployed the catalogs which we had in the European regional grids through Punch. And the second crucial step in setting up ILDG version 2.0, ILDG 2.0, was that we changed the authentication authorization infrastructure to use an Indigo IAM, which was developed for the LHC experiments, basically at INFN, and which also generously hosts our dedicated instance of this identity and access management, and which gives us very powerful provides us the ILDG worldwide user registration and management, but also the possibility for the central access control. So the architecture of ILDG is illustrated here. There's this central identity and access management instance of this Indigo IAM at INFN. Users log in, authenticate with their home institutions as IDPs. And then all regional grids obtain their authorization and authentication information from the IAM. Each regional grid implements at least in theory, its own metadata catalog, its own file catalog, and one or more storage locations, depending on how its local infrastructure is organized. So this is a very modular architecture. It's not a monolithic framework, also very flexible, and we are using it without any mandatory graphical sugar. We can simply typically use it just by standard web clients, which are available on any host. So you don't need any particular client software. But of course, you would make it more comfortable, or can make it more comfortable by setting up corresponding wrapper scripts, depending on your taste. There's one important point which I think is also quite innovative and maybe ahead of some other setups with the Indigo IAM, simply because of the fact that in ILDG we were in the lucky position that the old setup was basically dysfunctional, and we could afford a period of a few months where we completely restructured our services, switching from the old setup, which used grid certificates to OAuth 2 tokens. And in this way, now we can support fully embargo restrictions. And I would like to at least briefly sketch the idea of the access control, which we implement in ILDG on this global worldwide level. I mean, of course, in any access control, the challenge is that you have a complicated many-to-many relation between hundreds of or thousands of users and millions of files or resources, and then in principle also for any action, reading, writing, listing, etc., you have to define which user is allowed to do what. And what typically is done is you break this down into two steps. You map users into groups and then define what the groups can do. This makes the whole setup consistent, at least with GDPR, because you don't have to carry personal data to the resource providers, to the resource services anymore. However, the mapping between what members of a certain group can do on certain files, that's something this policy decision is taking place in the resource servers, in the storage elements, in the catalogs. And so you have this distributed again all over the world, and you have to keep this consistent. And so what the step forward which we made in ILDG now is to break this, to switch to a completely capability-based access control model, where you break down your relation into three relations. Users are mapped into groups. Then groups, you define what the members of certain groups, what capabilities they are allowed to have, and then you transport these capabilities to the resource servers. But the definition, the mapping of what what capabilities they have, this is done in a unique, can be done in a unique central policy decision point, which in our case is the Indigo IAM, which provides this feature, or in a dedicated add-on access control service. And then only the capabilities need to be encoded into the tokens, which are, for instance, in the scope claim, which are then transported to the resource servers, and there the decision can be done by very regular, simple rules. So for instance, in our case, in the access tokens use standard WLCG scopes like storage, modify, storage read, etc. But also we also wanted to keep separate control on the data and the metadata. So we also introduced scopes like metadata write. And the nice thing is all these scopes are parametric in a path, with a path parameter, and then one just needs very simple rules at the resource services where the actual files or metadata documents are stored. what path parameters you need in your scope in order to do what. And in case of a storage element, this is fairly obvious, mapping to the path of the storage URL or respect to some base URL. And similarly, you can do it in the file catalog, and for the metadata catalog, we implemented different options. You can either do it from an ID, which may have a path structure, or completely user controlled. And then, of course, if you want to access something, a file at some storage element A, B, C, D, and the base URL starts here, then you need a scope which either has access to all subtrees or specifically specifies to which files or objects you have access or you don't have access. And the interesting thing is that of course, this completely token-based access control eventually should also be extended to the definition of the permissions itself. So the definition of groups definition of group membership is also a resource like a file or like metadata. And also the scope policies, which define what permissions members of a group can have itself can be treated in a similar way. And this makes the whole thing hierarchically, but this is still something under development, but in principle, very powerful. And there are a number of extensions which we are considering in ILDG beyond the plain, let's say, requirements of the Lattice community. For instance, in our case, ingestion of the metadata is very simple because it typically is coming from the production codes of the individual collaborations. The input parameters simply from them you can derive a large part of the metadata, like parameters, simulation parameters, physics parameters, algorithm settings, etc. But for other communities, it might be interesting to think of some kind of automatic ingestions. In our case, graphical user interfaces are not so very useful because I wouldn't want to use a graphical user interface to upload or mark up thousands or 10,000s of configurations. But in other cases, graphical user interfaces could be helpful and can be simply attached to the catalogs. Also harvesting, also automatic file transfers between storage elements if you want to replicate your data set on two different storage elements or in two different countries, for instance. We also came up with solutions for very lightweight storage element, which in principle allows you in this framework, in this authorized framework, to even basically include your laptop or expose it as a storage element. And as I said, there are developments in progress to also make the definition of the policies, the access policies, in a more hierarchical, for instance, project, community project, experiment structured way. These are extensions which one could add. The important thing is that one has conceptually this consistent global access control for all these services. So let me summarize. And thanks to Punch for NFDI efforts in developing the new catalogs, and thanks to the new powerful identity and access management from INFN, we have now a fully working refactored version of ILDG. We are currently starting with new uploads. There was legacy data, which is 20 years and more old, of still something like 500K configurations, but this is now expected in the next 2 years or so to grow by a factor of 10, because over the last years there was a huge pile up of data which was not made or was not possible to share among the collaborations due to the restructuring of ILDG. And this provides a relatively modular, fair infrastructure, a fair framework for distributed data management. also of large data, including a very fine-grained, potentially very fine-grained access control, and very flexible and modular to be extended with additional services. And this is also potentially interesting for other use cases beyond Lattice QCD, for instance, small and medium-sized experiments. And this is currently being explored, for instance, for some axion search experiments and for one smaller experiment in radio astronomy, test beam at DAISY, etc. And of course, we are happy and would be happy and open to further exploit synergies with other communities for, let's say, this technical setup. And as I said, I've not talked very much on the metadata aspect because that was solved in our community, luckily, more than 20 years ago. And of course, is something which is always very specific to the individual communities. Thank you.
So thank you for this very interesting presentation and insights. And we do actually have a few questions in the chat. Already see a very general question in the end. Will the slides be made available? And I mean, I can't speak for you, but I think if we'll share the slides and also recording after the end of the workshop. Okay, but back to topic. The first question is, what ontologies and controlled vocabularies do you use to annotate metadata?
I would say we don't have a very formally defined vocabulary or ontology. In our case, I think it is. I mean, it's the ontology is given by the theory. We know what QCD is. We know what a mass of a quark is. We know what a coupling constant is. And we know in our algorithms what kind of parameters you have, time step sizes, number of auxiliary fields, precisions of solvers, etc. So this is rather self-explaining, but we are aware that we lack something like a better and well-defined vocabulary.
All right, thank you. And we also have a second question, which was actually answered in the chat, but for the sake of the recording, I'll still read it. Is the ILDG schema published somewhere as XML or Shackle or another
Yes,
open format?
you find the always up latest version or the official version. You can download it first of all from the catalogs. I mean, all our catalogs are public. You can simply with a curl command or with a web, on a web page you can access the metadata because it's fully public. And on the ILDG web page, under specifications, you also find the XSD files for the two schemata.
Great, thank you. So that's all the questions that I see in chat right now. Again, we'll have time to discuss further after the next use case. Still no questions? Okay, in that case, I'll say again, thank you for the presentation. And we get to the third use case. I just realized I should have used the ontology question as a transition, but I missed this opportunity. For the last use case where we go a little bit away from the experimental data, more to the literature data, and what can we do with that? With a short introduction from Alexander Sommer-Behr. Please, Alex, up for
Thank
the
you.
last round.
Yes, I'm currently trying to share my screen, and it looks like you are seeing what I'm seeing right now. So welcome from my side. I'm from NFDI for CUT, obviously, as it's also stated here on the slide. And today I want to talk a bit about the work from me and my colleagues Mark Volkenrath and Henrik Borgelt from TU Dortmund University. And yeah, maybe let's start with a brief motivation why we are doing what we are doing. So yeah, as maybe all researchers know, systemized and structured literature reviews are necessary, but often very time-consuming. And thus we saw the need for structured, sorted data on catalysis research, because this is what we often do not really have. And yeah, this also will or can simplify the information retrieval for our catalysis research. And also what we think it might be useful in the end would be the identification of research gaps. So we thought, okay, maybe it's a smart idea to structure data and knowledge from text in knowledge graphs, which in turn are based on different ontologies in such a way, as you can see here on the right-hand side, where we have some text, maybe some smart tool detects for us that we have some sort of catalyst and then splits it up in a knowledge graph somehow like this, and in such a way that we can afterwards maybe by a SparkQL query, for example, extract the data that was generated for us. And yeah, basically this is what motivated us to start with the first try. This was done 2023, 2024. So when ChatGPT was available, but for us at least a bit too expensive to deploy. So we used the tool called Catalysis IE for information extraction. That's an information extraction tool, pre-trained model that was that we found that was shared via a GitHub repository, and that was able to categorize text into 6 categories: catalyst, reaction, characterization, reactant, product, treatment. For those of you not that familiar with catalysis, those are basically one of the most important terms, I would argue, that researchers are searching for in papers, and also terms that are usually not really recorded in metadata. And what we did then was not only to take this model, but also we tried to train it even further for our purposes, do some text mining with it based on DOIs of literature, mapping terms to the ontologies, pre-process the entities, extend ontologies when necessary with new classes that were introduced basically based on the information that we found in our text, and obviously populate the ontology in order to get a knowledge graph that we could then automatically also query, not automatically, that we automatically extend the ontology to a knowledge graph, which we can then also query with SparkQL queries. And then we also did a kind of back loop to our text retrieval, because we found by that new keywords to search for new publications in the similar field of studies. So baseline on this would be that we try to structure literature data in knowledge graphs based on ontologies. And now I want to take you with me on the journey on how this looked like basically on text mining level. So what you usually retrieve from the publishers are abstracts, basically like plain text written here. And our tool was able to basically identify some of the words that you can see here highlighted also. And after splitting the text in sentences, obviously this is also needed for Catalysis IE to work. We were then able to use our prediction model that was based on Catalysis IE in order to come from this human readable but not really machine readable abstract to this code form where you can see here, for example, everything that I marked before in yellow would be determined as having something to do with the catalyst or being the description of the catalyst itself. We have the same in pink here for reactions. And for example, treatments. In this abstract, no treatments were described, but in principle, the tool is also able to detect treatments. Also, same with reactants. Here, naphtha was detected as reactants, and product list was also given here, as you can see here. And characterizations methods in principle could also be detected, but were also not really described in this exemplary abstract here. The nice thing that this transformer gave us was that we were able to automatically extract basically a dictionary of more deeper information on what we are looking at on the abstracts that we had here and give it out as a JSON file. Then we proceeded with a semantic modeling. For this, we use the ontologies that you can see here and also another ontology, I'll come to that later, that we designed to describe reactions in a bit more detail. So we had it for the BFO, the basic formal ontology, as a top-level ontology, and use the allotrope foundation concepts from the allotrope foundation ontology, the key by molecular process ontology, and name reaction ontology in order to extend our knowledge graph even more a bit before querying it afterwards. So how did this look like in the end? I brought with me this small sentence up here, where we have in this work, we develop a high-performance rhodium-based atomically dispersed and rhodium silicon dioxide catalyst for olefin hydroformylation. And here you can already see, okay, some substances are in there. And this we were able to exemplarily for this year construct a knowledge graph as follows. We have a class called publication. So wherever this example came from was then asserted to publication 1 as an instance of the class publication. We have then also, because of this, introduced our rhodium-based atomically dispersed catalyst, which in turn is an instance of the chemical substance and mentioned in this publication. And it has a role of the atomically dispersed catalyst role, which is in turn the instance of the respective class, which was introduced newly by our algorithm as a subclass of catalyst role. And we also have the rhodium atom that was mentioned in the publication. It is an instance of the KB class rhodium atom. And for sure, the catalyst role and support role have also respective instances, which can then be the role of the rhodium supported on silicon dioxide. So the carrier material, which has the support component silicon dioxide, which is an instance of the KB class. And we also were able to then also link the rhodium atom to our carrier material, so to our active catalyst, so to say. And we're able to map all these individuals to the publication where it was mentioned. And also for sure, our catalyst is also an instance of a chemical substance. This is just a small example, small insight on how our semantic modeling looked like in this regard. And with this, we did kind of roll out, so to say, from our tool on 2 data sets. One was on 19 publications on liquid and gas phase hydroformylation, so chemical stuff. You can just remember if you have not that much for chemistry, just one kind of reaction classes was investigated in these 19 publications. And in the second data set, the 26 publications, methanation of CO2 was investigated. So another class of reactions with different catalysts at hand. And before that, we also retrained or trained our model a bit more, such that it was more focused, but more able to extract the classes that we really needed from the respective texts. And with this, you can see here we constructed our initial ontology. We have some metrics in here. Maybe look at the classes. So we have in our initial ontology, we had like 3,000 classes. And after the dataset 1 was digested and the ontology was extended, we came up with class estimations for 300 more classes and about 200 more classes for our dataset number 2. And we also included much more instances in order to construct our knowledge graph accordingly. With this knowledge graph at hand, we found for the dataset 1, based on the 19 publications, 731 publications that were similar in content to the 19 publications that we had basically as an input, and were able to generate the knowledge graph automatically. So why did we do that? Or what was the more purpose of this? I brought with me here a small excerpt from Protégé, that is an ontology visualization and editing software for those who don't know. Kind of nice. You can see here in the core our publication number 18 and all the links with the relationships to the different other instances of the respective classes. And if you take a look into some annotations, for example, of I'm missing it, let's say from one of these individuals here, you can see that we not only asserted this as a chemical substance, and it's mentioned in some publication here, and it has the role of catalyst role, but by including our ontology called React for Cut, we were also able to directly deduce the information that because this individual was connected to the rhodium atom individual, there must be also some component of rhodium atom in this component in here. And also the same goes for cobalt atom and aluminum oxide and so on, and that it has the catalyst role. And this in turn helps us, on the other hand, to search more efficiently for the publications and for different carrier materials that contain, for example, the rhodium atom, even though it was not asserted directly. And yeah, what's more, we have also included in our knowledge graph more information on the publications. For example, the abstract is a plain text for humans to even read about it a bit more. And we also have included a DOI in here for sure as a more persistent identifier. And with this, I also want to show you a brief kind of live-ish demo. I pre-recorded it where we already deployed this knowledge graph in a server at NFDI for CAD, thanks to the HLRS. And we also provided for the users, for the end users, so to say, predefined queries, similar to what you can find on Wikidata, for example. And you can see here different functionalities. You can, for example, search for keyword. And then down below in the SparkUI query, you can also edit the keywords. You can then obviously see also the results. And if you want to edit a keyword, I think I'm doing it right now in the video. Yeah, there you can change the from methanation to hide like an arbitrary search string. And then after I click also run, you can see there we only find the hydrogenation publications that were conforming to the query. And yeah, because we are doing linked data, you can not only find also the same reactions as in a certain DOI that you can specify there. So if you want to have same reactions as in this DOI, all the other publications in there, they are listed there. You can click the hyperlinks leading to the papers. And also here, for example, we are searching for reactions with methanation or papers that are describing reactions with hydrogenation. Then you can also run it and click on the links there and go through the papers. I think I showed no, yes. So then you can also directly have a look at the actual paper rather than just reading the abstracts. And yeah, clicking away all the cookies is important too. But then again, you can see that we try to give the Catalyst community a bit of a more useful handling of all this knowledge graph technology, because we noticed in NFDI that this is sometimes a bit tricky to do for the end users. Yeah. Next up, we thought, okay, maybe can we use all of this for conferences? So can we get more tangible results for the community with our knowledge graphs, because they are more like backend software for us at least. And we try to get to the community of Catalyst scientists and hook them up basically on all the semantic web ideas. And with this, a colleague, Hendrik, he went out and tried to organize the abstracts of the Catalytica Tagung in Weimar. That's a conference that's annually taking place in Weimar, obviously. And for the conference of 2024, with the kind help of Decima, we got the 217 abstracts in PDF format from all the people going to the conference and presenting either posters or talks. And then with large language model assisted extraction of authors, affiliations, title references, keywords, we were then able to, obviously after doing some manual annotation and data cleaning, to also post it on GitHub as a graph user interface. The link is posted down below on the bottom left, and you can also scan the QR code if you have your mobile handy. So there you can also go through it, go through all the stuff that is presented there, and go through all the publications. And yeah, obviously, when it comes to doing something with literature data, you cannot go around data cleaning. So the colleague not only did the data cleaning, but he also programmed himself a small custom graphic user interface where you could edit past all these entries that were not detected by the large language model, and also to check whether or not the information posted in there is true. And also because different people describe the institutions differently, as you can see here, for example, with Fritz Haber Institute of the Max Planck Society, someone described it in German, the other one described it in English. And so it's the same institute, but obviously in the PDFs of the abstracts, they were listed differently. So there was also a bit data cleaning necessary. And afterwards, so why we did do this, it was we are able to basically show the people which submitted publications are dealing or are made from which people, because not everyone maybe attends the conference. And also you can see, for example, from different people which affiliations they have and maybe with which other people or which who other people they are working together. And also which other institutes maybe are associated to them. And yeah, so this was kind of nice for us to show basically who's working together with whom in the scientific community, and maybe to give some potential of networking for the people. And with this, I'm coming slowly to an end of my talk. So maybe like a brief outlook. So what's next? Maybe can we extend our tools to more than just publications? For sure, the colleague of mine, I think he's also here today, Mark Völkenrath, he's trying to look into automated metadata extraction, where we want to use large language models to extract metadata from publications, extend our own NeXus-based metadata standards, and enhance our React4Cut ontology that was used to give the assertions in the knowledge graph before. And also, we try to generate concepts more efficiently and use the LLM also a bit for suggestions and to help domain experts validating if their definitions in ontologies are okay enough for us as ontologists to look over it and so on. And yeah, this is also the current extraction workflow that is in development. We try to start from legacy data, do some metadata extraction, in order to get some semantic annotated metadata out of it and match it to our schemas that we are developing currently. So starting from the arbitrary data, we try to get semantic chunks out of it and the extraction scheme, which then in turn is used to extract the metadata from the arbitrary data, find the terms in existing vocabularies and ontologies, or maybe even our metadata standards, to then use them to validate our fields. We are focusing there on DCAT-AP, which is JSON-LD, sorry, not JSON-LD, LinkML based. And if the validation fails, we then try to do a guided rerun with human input, maybe even, or try to convince the LLM to try again, so to say. And if this is successful, then we get our structured metadata out of it in LinkML format, which we then can use as semantic rich data for inclusion in future knowledge graphs. So to summarize my talk, I presented to you how we are in NFDI for Cut trying to use natural language programming based and natural language processing based and large language model based knowledge graph generation for textual data and related data for the catalysis field, and to how we are trying to automate metadata extraction from legacy data, from publications, research data, and for the extension of our metadata standards. Yeah, what is also up next is the further development of our kglit4cat tools and the deployment of our tools as services in our database, for example. And with this, I'm coming to a close. Thank you all for your attention. And if you have any questions, feel free to ask them. Thank you.
Okay, clapping hands exploding again. Great.
Great. Maybe I stop sharing my screen because then I can see you better.
Yeah.
Yeah, right.
So thank you for the presentation. Indeed, we have one question already. How do you handle the potential case if a term is found in different vocabularies with different definitions?
Yeah, usually by user input. So if we have this, we are getting multiple outputs of the class areas and the description in our tool, and then it asks the end user basically, or the guy in front, so me in front of the PC, okay, whether or not to use this or that class. And sometimes even mappings are possible then for the classes, at least in our knowledge graph, so that we can, yeah. I hope this answered the question.
All right.
Ah.
New question coming up. Thanks for the great talk again. How do you plan to evaluate the results from LLMs?
Yeah, this is, I think, one of the more difficult parts because without getting too much into all the manual work, you need to do some kind of automation. And that's where the DCAT AP plus standards are coming in, because with them you can validate whether whether or not the output of the LLM or the afterwards suggested output of the LLM is in the correct format, and if the schema is fitting, or if the data, sorry, let me phrase it again, if the output data is fitting to the schema. And with it, you get a kind of quality control. With regards to hallucinations, you will need to rely on human input, I think, and human validation. But in principle, why we are also doing this, I mean, you could say then, okay, why are you doing it in the first place? Users can input their metadata by themselves then and would be done. The general idea here is to extend our metadata standards, obviously far beyond the Dublin core standard. And for us, at least, it's way too many metadata fields that are sometimes also way too specific. And users do really not like to fill out endless formulas. So we try to help them there to deliver some tools that are doing this automatically, and at least LLM assisted, so they can read over it and think, okay, this is right. Maybe there I need to correct something, but maybe at least 80% of the data they put in our KG-lit forcat, in our KG-lit forcat is detected correctly, and they can use it afterwards as a metadata file to publish in the repos.